Hi, this is Misty, and these are the notes on energy. So the first thing we need to do is we need to go ahead and define energy. Energy is the ability to do work, which we also define as the ability to cause a change. So if you think back to our definition of work was when you take a force and you apply it across a distance. If I'm actually able to go ahead and move something across a distance by applying a force, then we said that I've used energy because I've been able to do work. So let's go ahead and let's look at the different forms of energy, and these should be reviewed for you. There's two basic forms of energy: kinetic energy, which is energy of a moving object. So an example for that is a bowling ball rolling down the lane. The other form is potential energy. And an example of potential energy, potential energy, stored energy, or energy of position. And energy of position sounds pretty funky, but this is what that means. So here's an example. If I have a rock on a high shelf, that energy is stored because the rock is on a high shelf. That's a high position, and it might fall down, giving it a lot of velocity as it falls. Another example of potential energy is a battery that's in the package. So if you've got a battery, it's not hooked up to anything, it still has that energy there. We would say that that's potential energy. So how do I find kinetic energy mathematically? Well, here's the formula. Kinetic energy is 1/2 mass times velocity squared. So let's look at an example. If I have a ball that's rolling at 5 meters per second, and I tell you that that ball has a mass of 10 kilograms, then I could plug in 1/2 mass 10 times velocity 5 squared, and that's going to go ahead and give me the kinetic energy is 1/2 times 10 times 25, and that equals 125 joules. Joules are the units that I use to represent energy, just like I use them for work, because work was kind of energy's the ability to do work. We're using the same units. So again, we're using joules. How do I find potential energy? Now this is an object that's not moving, so an object that's high up, and this is gravitational potential energy. The potential energy something has due to gravity, and there's some other potential energy, but we're not going to talk about that today. So we're going to find the gravitational potential energy by multiplying the mass times the gravity times height, where remember gravity on Earth is 9.8 meters per second squared. So if I have a rock that's 10 kilograms sitting on top of a 50-meter cliff, potential energy is 10 times 9.8 times 50, mass times gravity times height, and that's going to give me a potential energy of 4,900 joules, which is quite a bit of energy. One of the other things we talk about is how mechanical energy is the total amount of energy that's present in a system. It's the total kinetic energy plus the total potential energy. So if I want to find the total energy, I just add kinetic energy plus potential energy together. That's pretty simple, but if you don't actually know how to solve for it mathematically, it can be pretty confusing. But it's just a straight addition. You just do potential plus kinetic. So as the potential energy goes up, the kinetic energy is going to go down. Now I want to show you an example of that. Let's look at a roller coaster. So if I draw my roller coaster, and I draw my little cart on my roller coaster, here's my questions. Where does the cart have the most potential energy? So I think everybody would tell me that the cart has the most potential energy right there at the top of the first hill, because that's the highest hill. So it's mass times gravity times height. The mass of the cart doesn't change, gravity doesn't change, but the height changes. So we go to where the highest hill is. So that's where there's going to be the most potential energy. So where is there not very much potential energy? Well, right there's not very much potential energy because the height's pretty much zero. So we would say there it basically has zero potential energy. What about right there? Right there it's going to have some potential energy because the height, it's about halfway up the hill. It's got some height, right? So it does have potential energy, but the potential energy there is decreasing. So now let me ask you a different question. Where does it have the most kinetic energy? Remember, kinetic energy is 1/2 mass times velocity squared. So I would have the most kinetic energy where? Where is it going to be going the fastest? I think you know it's going to be going the fastest at the bottom of the hill. So what happens is as the potential energy is decreasing, the kinetic energy is increasing. So let's go ahead and label the other two spots. Here at the bottom, I would have a very high kinetic energy. Up at the top of the hill, it's not moving, so my kinetic energy would be extremely low. Let's say that again. Potential energy and kinetic energy are going to be inverses. Now remember from the very beginning of our notes that energy is the ability to do work. So work is equal to the kinetic energy plus the potential energy. But what if we look at a situation where an object's kinetic energy is 0? Well, that would mean that work is just equal to the potential energy. And this is a bit of an oversimplification, so let's go ahead and look at specifically what I'm talking about. We use that fact that work is the ability, or energy is the ability to do work, to write the following equations. Work is equal to the total change in potential energy. So if I move a rock from the top of a hill to the bottom of a hill, the amount of work I've done is simply the force times the distance. But I can calculate that by also finding what's the potential energy of the rock, mass times gravity times height. I know that sounds funky, but trust me, I can go ahead and do that. Work is equal to mass times gravity times height in that situation. Conversely, what that's going to mean is that if I have an object that's moving, I can go ahead and use the formula work is equal to the total change in kinetic energy. So if it was stopped and then it speeds up, I can find the kinetic energy, and that's going to tell me how much work was done. So I could do work is equal to 1/2 mass times velocity squared. And you're going to be using these formulas with the work equals force times distance formula when we start looking at some other problems later.